Alright, in this part of the review, this is looking at a written out sum and converting it into sigma notation. Probably one of the more tricky things that could be on the test. We have several problems, or we've done them before, where I give you the sigma notation and then you expand it out and add the terms. Here we're going in the opposite direction. I'm giving you the expanded out terms and then I'm asking you to convert it into sigma notation. So here we have number 9 and number 10, and those are the only two. And I kind of wish I had a different example that was a little bit more straightforward. But when you're doing these types of problems, the first thing you want to do is find a formula for the series or the sequence. Find a formula for the sequence of terms. Now in number 9, I made that very easy because if you look at the very last term, I give you 2 to the n plus 1 over 3 to the n. That right there is your formula. And what I'm doing is I'm just plugging in different values for n. For example, if I plugged in 3 for n, if n is equal to 3, I would have 2 to the 3 plus 1, which is 2 to the 3 plus 1 over 3 to the 3. 2 to the 3 plus 1, that'd be 4. And 2 to the 4th is 16. 3 to the 3rd is 27. And that actually gave me this term right here. So what I've done at the end is I've told you what the formula is, which makes this problem a little bit easier. So my formula is 2 to the n plus 1 over 3 to the n. So I know it's going to be the sum of 2 to the n plus 1 over 3 to the n. And so I have my formula, and now the challenge is knowing where am I starting. I have to know what's the first number for n that I plug in. What do I plug in at the very beginning to give me 2, and what do I plug in at the very end? What's the last thing I plug in for n? So I've got to find out what my starting n is, and I've got to find out what I end with. Okay, the starting one, you really just kind of guess and check. Normally you would think, well, it's my first term, so n would be 1. So let's try n equals 1. But if I try n equals 1, now I'll just keep it right there. If I try n equals 1, then I would have 2 to the 1 plus 1. So I'd have 2 to the 2 over 3 to the 1. And 2 squared is 4. 3 to the first is 3. And when I plugged in n equals 1, that actually gave me my second term. Well, since 1 gave me my second term, that means the one right before it, we just found out that this is n equals 1. That means this one has to be 1 less for n, so that one's got to be n equals 0. And so we'll test n equals 0. And when I do that, I have 2 to the 0 plus 1, which is 2 to the 1, over 3 to the 0, which will be 2 to the first, which is 2, 3 to the 0 is 1, and 2 over 1 is 2. So that means I am starting at n equals 1. All right. And then the tricky part for this one, and this is, I kind of think it's a bad problem. I wish I hadn't done n plus 1. I wish I put like 8 plus 1 or something like that. But I don't end at a number. The last thing I plug in, the very last term is 2 to the n plus 1 and 3 to the n. So the very last thing I plugged in is actually the letter n. So I'm going to stop with n. So I'm going to plug in 1, then I'll start. What did I just do? This is a mistake. I start by plugging in 0, not 1. N equals 0 gave me my first term. So I'm going to start with n equals 0. And then I would plug in 1 to get 4/3, which I have right here. If I plugged in 2, I would get 8 over 9. If I plugged in 3, I'll get this one. If I plugged in 4, if I plugged in 5. And then at the very end, I'm plugging in just n. Now this is why I don't like this problem, because I actually have a conflict of variables. Since n is where I'm stopping, that means I cannot use n in the formula. So I'm simply going to erase the n's here, and I'm going to turn them into something like k, or you could use r or whatever letter you want to. But my formula, I'm going to say is 2 to the k plus 1 over 3 to the k. Same idea, except I'm just using k's instead of n's. And then we'll start with 0, and we'll go all the way up to n. And that is our formula. So maybe I'll just rewrite it where I don't have all those extra things all over the place. So 2 to the k plus 1 over 3 to the k. And that would be your final formula in sigma notation. Let's do one more. 1 minus 1/2 plus 1/3 minus 1/4 plus a bunch of missing numbers, and then plus 1 over 11. And this one's going to be a little bit trickier because my very last term doesn't tell you what the formula is. We have to figure it out. So when I'm looking at something like this, especially if it's a fraction, what I'll do is I'll look at my numerators and then I'll look at my denominators separately. So let's look at my numerators, and this is very easy for the numerators. My numerators are 1, 1, 1, 1, and then I skipped a lot, and then I had 1. So I'm going to go out on a limb and say that my numerators are always 1. And then I'm going to look at my denominator. And I'm going to look for a pattern in my denominator. They start with, well, it's an understood 1, so I start with 1. My denominators are 1. My second one is 2. My third one is 3. Then 4. Then we skip a lot, and we end at 11. Now this one's a little bit more difficult, not a whole lot more difficult. I mean, it's a lot more difficult than 1, but they're going up by 1s each time. And what I see is that for my first term, if n is equal to 1, my denominator is 1. For my second term, my denominator is 2. For my third term, my denominator is 3. For my fourth term, my denominator is 4. So what I'm seeing is that my denominator is simply equal to whatever the n value is. So I would take this information and say that my numerator is always 1, my denominator is always n, starting with n equals 1. So I know that this is going to be the sum of the formula 1 over n, except I've ignored one little part. The other part of this, it's going to make it a little bit tricky, is that my first term is positive, my second term is negative, my third term is positive, then negative, then positive, and then we skip some and we finish with a positive. But this is also an alternating sequence. And if you have an alternating sequence, the way a formula will alternate is if there is a -1 to the n power or -1 to the n plus 1. One of those two must be part of the formula. And that's going to make this series alternate. And the way that I'll figure that out is I'm simply going to guess and check. So let's pretend that -1 to the n is right. Well, then my formula would be -1 to the n, and then I still have 1 over n. So -1 to the n times 1 over n. If I plugged in 1 for n, if n is equal to 1, -1 to the 1 times 1 over 1 would be, let's see, -1 to the first is simply -1, 1 over 1 is 1, and -1 times 1 is -1. All of this is when n was equal to 1. And then I would try n equals 2. Okay, so if n is equal to 2, I would have -1 to the 2 times 1 over 2 for n. And I'm just checking this to see if it works. -1 squared is +1 times 1/2, and 1 times 1/2 is 1/2, and that would be my second term. While I'm looking at this, and -1 to the n times 1 over n, it is alternating. I started with a negative, then 1/2 was positive. If I plugged in 3 for n, I would get a negative, but I'm looking at my formula, and my 1 should be positive, and my 1/2 should be negative. I have it backwards here. That means this is not right. I don't like that because I want to start with a +1 and then have a -1/2. Well, that means the other option should be right. So -1 to the n plus 1 times 1 over n should work, and we'll test that out. So now I'm going to test that. Let's see, so if I plugged in n is equal to 1, So for n is equal to 1, I would have negative 1 to the 1 plus 1 times 1 over 1 for n. Negative 1, 1 plus 1 is 2, so that'd be negative 1 squared times 1. Negative 1 squared is positive 1 times 1, which is 1. So when n is equal to 1, I got positive 1, and I like that because I should start with a positive 1. So that really lets me think that n equals 1 is correct. And then just to be doubly sure, I'm going to plug in 2, negative 1 to the 2 plus 1 times 1 over 2. Negative 1, 2 plus 1 is 3. Negative 1 cubed is negative 1 times 1 half. Negative 1 times 1 half is negative 1 half. That's what I got when n is equal to 2. And that does match what I needed. I need a positive 1, negative 1 half, and I got a positive 1, negative 1 half. That means this is the one that's going to be part of, this is going to be my formula. So I'm going to adjust my formula right here. Instead of just 1 over n, it's going to be negative 1 to the n plus 1 times 1 over n. And then the very last thing we have to do is find out where does n start and where does it end. And that I'm going to look at my denominators, and I noticed that when n was equal to 1, my denominator was 1. When n was 2, my denominator was 2. At 3, my denominator was 3. So I'm comfortable saying I'm going to start with n equals 1. So if I plug in 1, then I would have 1 over 1. That would be my first term. If I plugged in 2, 1 over 2 would be my last term. And then I end with a denominator of 3. So I'm finishing by plugging in, I'm sorry, what did I say 3 for? I'm finishing by plugging in 11 for n. So I'm going to go from 1 all the way to 11. And then I'm going to add all of those terms. This is our sequence. Unfortunately, the two problems I put on the review for this were both kind of tricky. But this is how you would do how you would convert an expanded sum into sigma notation. So there you go. Happy Friday.